So our next speaker is Mikko Rantala from Glaston. So let's say he's a local in Tampere. And Mikko, so he holds a Doctor of Science. So he did his studies about heat transfer. And he's a specialist at Glaston when it comes to thermal engineering. And he's also the patent specialist for IP questions. And so he's been dealing with heat treatment, especially for the glass industry, of course, since 1997. So it's many, many years of experience. And he has also managed Glaston's HT patent portfolio in the last couple of years. So today he will present about, so his title is Predicting Interlayer and Glass Temperatures in Automated Glass Lamination Process. So please welcome Mikko, and Mikko, the stage is yours.
Thank you. So, the subject of my presentation is flat glass lamination line. Here you can see the whole line, but my presentation focuses on only to oven and the nip roller after it. The aim of the process is to get air out from the interfaces between glass and interlayer, and to get bond between the layers. But the bond is then finished in autoclave. Here you can see the operator selecting heating recipe for the lamination oven. He must be talented and his working time cost. And if he makes mistakes, then we get waste, the waste cost. And also the electricity cost. So the motive behind my research is saving. And my aim is to save from all of these possibilities. Today, the heating is monitored by measuring the surface temperature after the oven and before the nip roller. And the interlayer manufacturer gives following guidelines for the heating. This pyrometer temperature should be between 55 and 70 centigrades. But there's also a sentence that the surface temperature might mislead if we have thick sandwiches. But what is the temperature of the interlayer between glasses? Glass has poor thermal conductivity. And what if we have more layers, thick sandwich? What is it? So we have a problem. And the problem is that we want to heat the interlayer, but we don't know the interlayer temperature. And the prediction method aims to solve that problem. Next we'll show some examples of quality problems. Here, this glass has been too hot after laminating an oven. And then I take this area of this glass to this image. But there's also autoclaving between. This is not autoclaved, but this is autoclaved. Autoclave cannot save this glass. You see there is air bubbles. So, if the glass is too hot, we get waste. This glass has been too cold. And the same again. That area is here after autoclaving. And we get waste. It was too cold. Then what is the correct temperature for the interlayer nipple? What are the temperature limits? What is suitable? What is perfect? What is optimal? I think today we can't know that because we cannot measure the interlayer temperature online. We measure the surface temperature. But with the prediction method, we have just started to get information what the interlayer temperature is. So maybe after a few years we can tell something. What is the interlayer optimal temperature? What is suitable? What are the limits? But one thing is sure. Here at the tail edge, the upper limit is lower as in the rest of the glass because the nip roller guides the air when it presses the sandwich. It guides the air toward that direction. So a lot of air comes out of the tail edge. So it is critical to prevent that the premature edge sealing of the tail edge. So the problem is that interlayer temperature is known. And the more layers we have, more difficult it is to heat the sandwich to correct temperature. Here we have one interlayer, and here we have 4 interlayers. And if we get waste, it costs. So, by knowing the interlayer temperature before the heating, and somehow put that in a machine automation, we can save. There are choices for we can save. I already told in a second dia some of them. But there is also, of course, if we use less energy and get less waste, then we get less CO2 emission. So I will explain how we get smaller electricity bills. Today, often the worst recipe leading to successful result is used as always. Well, it avoids waste. If we get good recipe, then use it, we don't get waste. But maybe, and we have seen that we can drop the temperature. Maybe if we can drop it by 5 centigrade without any problems, then we can save energy. And also if we get less waste, then we can save from the electricity bills. About the prediction method itself, well, already 6 years ago in a GPD paper, I presented it, so I'm not going to that. But you can find more information for these references, and you can find them in my today's GPD book paper. But now this prediction method is tailored to this kind of oven. And in that oven, the heating is based mainly on forced convection. So there is a fan which guides air to these convection pipes and then blows the air as air jets against the glass surfaces. And so the main heat phenomena is convection, but we have also some radiation because these hot surfaces radiate against glass also. So this is the user interface of the prediction method. And my aim is that to create a code with which we can heat the glass as in a real oven. So we can virtually heat treat the glass as in our oven. That's my aim. So, after we have set the sandwich to the code, then we can select the heating recipe by selecting line speed and oven temperature exactly in the same way as in a real oven. And then pushing solve, it starts the heat reading. And it gives the result, it gives the predicted temperature for the interlayer at nipple roll, and also it predicts what the pyrometer will tell. And it also shows this as a thickness-wise temperature distributions and as a function of time, what is the heating speed of each layer. But it is clear, we can predict anything, but what is the accuracy? If the accuracy is poor, we don't do nothing about that prediction method. So, my aim is to increase this kind of accuracy ±3 in interlayer temperatures. But it's a tough accuracy but I think somehow I can prove that the accuracy is this. But it's impossible to prove that the accuracy is ±1 because it's impossible to measure the realization with such accuracy. Impossible to measure the interlayer temperature so accurately. So, to check the accuracy, then we need some kind of verifications. I have used two methods. The first method is that I have placed thermocouples in the interlayer between glasses, and then also on top surfaces. And then I have heated that sandwich in a full-scale lamination oven. And then same process is solved with the prediction method, with the same heating recipe. Here is one example of the results. In this case, we have two separate heating chambers. This is the first heating chamber. Our line in Tampere was that kind of 1 year ago. Now we have taken, because this is the nipple roll between the heating chambers. So it starts to cool when it comes out from the first chamber. And now, 2 weeks ago, we got it updated that there is no nipple roll anymore between the chambers, which is the typical method we sell for our customers. So the prediction matches quite well already to these color curves are the measured ones for the surface temperature, and this green one for the interlayer, and these black ones are the predicted ones. From this result we can also see two interesting details. For instance, that is the location, that arrow is the location of the pyrometer. And we can see that the surface temperature between the top surface of the sandwich and the interlayer, it was about 14 centigrades when the pyrometer measured the surface temperature. So there is a clear difference, even such a, this is not thick sandwich, typical sandwich, 6 mm glass. But if the sandwich is thicker, of course there is much more temperature difference. Also we can see here on this blue arrow that this line is the location of nip roller, but the temperature of the interlayer still increases after the nip roller. Can this nip roller be lower because the temperature still increases? I don't know. The other method is that we got data from the cloud storage for the lines in the world. So we got these blue dots which are the measured pyrometer readings from, this is one class, one dot is one class. And we got the heating recipe also. Well, you can, in my GPD this year's paper, you can read more about this comparison. But there are two problems. The data is still incomplete because it only tells the total thickness of the sandwich. The only total thickness can be measured automatically. So I have to make assumption that the sandwich composed of two classes with equal thicknesses and typical 0.76 PVP interlayer between them. Typically it matches, but not always. And also, I don't know what is the initial temperature of the glass before the oven. I have to again make an assumption that it's 20. But that is changing. We are starting to measure the initial temperature. But that cannot be fixed. Because there are no devices which can measure, online devices which can measure the thickness of different layers. The prediction method can be utilized in automation in a following way. It can be used as an auxiliary tool, maybe behind the main control panel of the oven. There is a second page, and the operator can open that if he needs help for the recipe selection. And it can be also coded as the method that warns if the recipe selection is incorrect, and then the operator can check it. And it can be also, this third choice is that it can be used as the temperature measuring device. So it just plots the predicted interlayer temperature besides the measured pyrometer temperature. But this last one is that it is really put fully in the machine. So, and maybe we can just tell that we want the interlayer temperature to be 55, and then the code handles the rest. But the problem is really that somebody have to set manually what is the thickness thickness of different layers, because there are no devices which can measure it automatically. Okay, thank you.